DNA is stranded, it has a nucleotide. 5 carbon sugar, 4 carbons in the ring. The 5th carbon is outside. A and T pair up and G and C form 3 hydrogen bonds. Always 2 for A and T, and 3 for B and C. And oh, did I forget to mention, number 3 of the 3 prime. 1 always has an OH group. Oh, number 1 is where we have the nitrogenous base, right? Come on, Tabitha, did you fall asleep in class? If only you'd pay attention like you do to that cute baseball player. Nitrogenous base is correct. Welcome to DNA replication, or what we call semi-conservative replication. So we have these whole strands of DNA, and they're not going to be broken up, simply. To put it into pop culture perspective, they're ride or dies. And to quote biology Brainery, the original DNA, the original parent strand, once it's broken apart, it's never going to come back together. And I tried so hard not to add a divorce joke, but I haven't been able to. So we've established that the DNA is never coming back together after it's been broken apart, and nobody said it better than T Swift. So if we want to stick with this analogy, who is the bad guy that comes in and breaks the parent strand, these 2 strands apart? His name is helicase, except helicase isn't really a bad guy. It's the enzyme that plays a crucial role in DNA replication. Strand in semi-conservative replication is a nucleotides are added 1 at a time. If we remember PEMDAS from middle school, multiplication comes before division. And how exactly does that relate to biology, you may ask? Well, in this case, we have to double the DNA before the cell can divide into 2 new cells. So essentially, the 1 double-stranded DNA undergoes DNA replication, leaving us with 2 double-stranded DNA, and hopefully they're twin twins, exactly the same as the other. But there's fraternal twins, right? Well, I'm gonna ask you guys a question now. What happens if there's an error in the replication process of DNA? Remember, A and T and G and C. So what happens if we get T and G, which don't bind?
Teenage Mutant Ninja Turtles! Teenage Mutant Ninja Turtles!
Mutation. Each chromosome in eukaryotic cells is incredibly long. Many origins of replication, the information is vast.
Okay, so there'll be multiple origins all happening at the
To copy the whole chromosome in a reasonable amount of time for the cell to divide.
Hey yo, DJ Professor, what we got in the single area where the 2 strands are pulled?
Replication, fork.
Typically, this is a bidirectional process. Starts at the origin, helicase has come and works in both directions.
You're now listening to SSBP Radio.
Ronnie, what's that? We got a caller in on line 1. Single-strand binding proteins. They bind to single strands of DNA and they keep them single. Sounds like my last situationship. So they don't hydrogen bond with the other strands, if you catch what I'm saying. They're only temporarily there, temporarily binding, and when the new DNA comes in, they're kicked out. So helicase pulls them apart, but SSBPs keep them apart, is what you're saying. Yeah. The 2 on each side, there's a replication bubble. Additional pressure is put on the coil, creates a problem called supercoil. Gotta find a way to ditch this so we don't get knotted up.
Topo isomerase is in the mix.
What it do, what it be? The phosphodiester bond between the 2 nucleotides? We breaking them. We'll get into the two different types of topoisomerase a different time, but for now all we need to know is that it's working ahead of the helicase and the SSBPs, and it's preventing the uncoiling so much that the DNA would tangle and become supercoiled. Okay, so I lied about the 20 seconds, but let's try to keep it under 6 minutes. DNA needs an enzyme called polymerase, which is going to read a template. So, it reads an A, brings in a T, nucleotide, reads a G, brings in a C, nucleotide. It's going to then build the new DNA, but there's a couple of problems. DNA polymerase has a couple of rules. One of them is that it can't work from scratch, and I'm not talking about my back. Thanks, Biology Brainery, for picking up my slack. Of course, the citations will be at the very bottom of this YouTube video. Thank you so much for this wonderful semester, everybody, and of course the pre-recorded lectures, they were fantastic. For DNA to do its job, it needs primase, or it's gonna be just a flop. Now we've got a primer, and I'm not talking about the type that you put on your face or on your car. I'm talking about the type that makes a short RNA section along a single-stranded DNA. This is the type of RNA DNA can build from scratch. Isn't that a knack? Now let's go back. It needs an open 3' end, and it'll keep on building in a 5' to 3' direction. Unlike Floyd Mayweather, it can read, so it's gonna read that template from a 3' to 5' direction. That's the way it reads it. McGregor, I love you. But because the strands are anti-parallel to it, it's gonna build a single strand of DNA from 5' to 3', 3' to 5' to 5' to 3'. Can you distinguish it? New DNA will be built from the primer. Both strands are copied at the same time, opposite direction, leading us to another problem. Oh my gosh, how many of those have we encountered? Leading and lagging strands. That is it for today, because the semester is over, so it's my 6 minutes of glory. And then, if you want to learn more, you should have read this, because our exam is due today. But if you haven't, then I'll show you the link to the lectures. Hopefully you'll hear more from me. Have a good life, everybody.